These are the answers to the Chapter 15 packet, Chemical Equilibrium. This picture is not an example of dynamic equilibrium. This picture is an example of static equilibrium because there is no movement back and forth between the two opposing forces. The rope is at rest. If we look at figure 1123 on page 443, we can see that in this particular diagram, eventually equilibrium is reached for the vapor pressure of the liquid because molecules are entering the liquid at the same rate that they are leaving the liquid. So it's a good example because the two opposing processes, evaporation and condensation, are occurring at the same rate. Another example of dynamic equilibrium is figure 13.8 on page 519. So we have an ionic solid that is being dissolved in water. So the rate of dissolving is the same as the rate of crystallization. So solid becoming aqueous and aqueous particles becoming solid. Two opposing processes occurring at the same rate. And so our definition of equilibrium on page 611 is that it occurs when opposing reactions proceed at equal rates. Section 15.1, the concept of equilibrium. Consider the reaction shown above in which dinitrogen tetroxide decomposes into nitrogen dioxide. The most obvious sign that this reaction involves equilibrium is the presence of the double arrows in opposite directions. N2O4 is colorless and NO2 is brown. And so on page 612 in your textbook, you can see that it starts out in the tube as N2O4. Eventually, as it's warmed, molecules of N2O4 dissociate to produce brown molecules of NO2. And at some point, the colors stop changing. Equilibrium is reached. So the tube starts out as N2O4, and over time, it gets darker because the molecules of N2O4 are decomposing to produce molecules of NO2. At some point, the color in the tube stops changing, and a student decides that the reason the colors stop changing is because the reaction is over, and all of the N2O4 molecules have been converted into NO2. We would disagree with this statement because even though the colors are no longer changing and that the concentrations of N2O4 and NO2 are not changing, this is still a dynamic process. Some N2O4 is always converting to NO2, and then some NO2 is always converting to N2O4. The two processes occur at the same rate. And so we say at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. Once equilibrium has been established for a chemical reaction in a closed system, the concentrations of reactants and products no longer change over time. However, this does not mean that the reactants and products stop reacting. The dynamic process means that some reactants are constantly being converted into products and vice versa. So once equilibrium is established, concentration of A is not necessarily equal to concentration of B, but the rate of the forward reaction is equal to the rate of the reverse reaction. A and B are no longer changing in terms of their concentrations, but it does not mean that they are no longer reacting. B over A does not necessarily have to equal 1, but the ratio of B divided by A would be a constant value. Section 15.2, the equilibrium constant. So we can look at, in both experiments, 1 and 2, a point is reached where equilibrium has been achieved, where the concentrations of all three chemicals no longer changes over time. We can also decide how they are similar and how they are different. So in experiment 1, we start with only reactants, hydrogen and nitrogen. Experiment 2 began with only product, ammonia, NH3. What makes them similar is that they both achieved the same concentrations of all three chemicals at equilibrium. And once they have reached equilibrium and their concentrations have not changed anymore, it is not true that the concentration of nitrogen is the same as the concentration of hydrogen or ammonia. They're all different numbers. They just simply are not changing anymore over time. Equation 15.7 and equation 15.8 are found on page 614, and you can see that the equilibrium constant expression is the ratio of concentration of products over concentration of reactants, and we raise the concentrations to the exponent, which corresponds to the coefficients in the balanced chemical equation. The Haber process is the formation of ammonia, NH3, from the elements hydrogen and nitrogen. So that reaction has 2 moles of ammonia on the product side, 1 mole of nitrogen gas, and 3 moles of hydrogen gas on the reactant side. So if we write the expression as concentration of ammonia squared divided by the product of concentration of nitrogen times the concentration of hydrogen cubed, we are plugging in the numbers that we have and the information we're given for this expression. The equilibrium constant expression depends only on the stoichiometry of the reaction, not the mechanism. The decomposition of hydrogen iodide represents the following balanced equation. 2 moles of HI decomposed to give 1 mole of hydrogen and 1 mole of iodine. So if we're going to do the expression for Kc, equilibrium constant expression would be concentration of hydrogen times concentration of iodine divided by concentration of hydrogen iodide squared. So now we're going to fill in the change in concentration for these 5 experiments. In experiment 1, the concentration of N2O4 has decreased by 0.7. The concentration of nitrogen dioxide has increased by 1.4. And it's the change in concentration that we're looking at. Notice that the change in concentration for NO2 is exactly twice as much as the change in concentration of N2O4. The absolute value of these changes, so 1.4 and 0.7, are exactly a 2-to-1 ratio because of the stoichiometry in the balanced chemical equation. Experiment 2, N2O4 increases by 4.51, NO2 decreases by 9.02. Again, the 2-to-1 ratio in the magnitude of these values represents the 2-to-1 ratio with respect to moles. Experiment 3, N2O4 increases by 1.9, NO2 decreases by 3.8. Experiment 4, N2O4 increases by 1.72, NO2 decreases by 3.44. And then finally, experiment 5, N2O4 decreases by 0.22, NO2 increases by 0.44. So as I've already mentioned, the change in NO2 is twice as large as that of N2O4. This is a direct result of the stoichiometry of the reaction with a 2-to-1 mole ratio between NO2 and N2O4. Now let's write the equilibrium constant expression. That would be products over reactants. So concentration of NO2 squared divided by the concentration of N2O4. We're now going to use that equilibrium constant expression to calculate the value of the equilibrium constant for all 5 experiments. So 1.4 squared divided by 9.3, 0.98 squared divided by 4.51, 1.2 squared divided by 6.9, and as you can see in all 5 of these expressions, Each experiment had very different numbers in terms of the concentrations of reactants and products, and yet we get the same value for the equilibrium constant, 0.21, in all 5 experiments. It's important to note that the value of the equilibrium constant at a particular temperature does not depend on the initial amounts of reactants and products. The value of the equilibrium constant only depends on the particular reaction and the temperature. And so the difference between Kc and Kp is that Kc has to do with concentration, molarity, and Kp has to do with pressure in atmospheres. On page 617, you can see the expression for Kp. It's still products over reactants, and you still raise the quantity to the power, which is the exponent coming from the coefficient in the balanced equation. We just simply use pressures as opposed to molarity values. So on page 617, equations 1514 and 1515 have to do with this relationship between Kp and Kc. So Kp equals Kc times RT, where R is the ideal gas constant, 0.08206. Temperature is the Kelvin temperature, and then raised to the delta N power, where delta N is the difference between moles of gaseous product and moles of gaseous reactant. Under what conditions would Kc equal Kp for a certain chemical reaction? Well, if delta N is 0, then there'd be the same number of moles of gas on both sides of the equation, so that delta N equals 0. Does the equilibrium constant normally have units? And the answer is no. And you can read on page 618 why we do not put units into this particular value. So when I say that the value of the equilibrium constant is 17 or 100, whatever that number is, it does not have any units. All right, section 15.3, understanding and working with equilibrium constants. When you have a very large value of K, the equilibrium lies to the right and the equilibrium is product favored. When the value of K is very small, equilibrium lies to the left and the equilibrium is reactant favored. So we're going to fill in the table with the missing information. The equilibrium constant expression for this reaction would be concentration of NO2 squared divided by concentration of N2O4. If you write the reaction in the reverse direction, now you have concentration of N2O4 divided by concentration of NO2 squared. So what's the value of Kc going to be? It's going to be the reciprocal of 0.21. So we get 4.8. If you flip a reaction by writing it in the other direction, then the equilibrium expression would be the reciprocal of the original. Here we have an equilibrium constant of 47. So because that is larger than 1, we could say that the products are favored, so that the side with the hydrogen chloride is favored because K is greater than 1. If we reverse the reaction, now the value of K would be 1 over 47. So because that value is less than 1, we would be favoring the reactants, but we're still favoring the side with hydrogen chloride on it. Here we have a reaction, so products over reactants, NO2 squared over N2O4, and now we're doubling the equation by multiplying by 2. So the new expression would be concentration of NO2 to the 4th power divided by concentration of N2O4 squared. Now what is that going to do to our value of the equilibrium constant? Not 0.21 times 2, but rather 0.21 raised to the 2nd power. So 0.21 squared is 0.044. So if you have an expression which is products over reactants, the new equation, if it's multiplied by some constant value x, is going to affect the equilibrium constant by causing you to raise that constant to the x power. So in this example, we have multiplied the original equation by 1/2. So the equilibrium constant would be 47 raised to the 1/2 power, so square root of 47. And then here we've multiplied it by 3, so you're going to raise 47 to the 3rd power, and that would give you 1 times 10 to the 5th power. Note that for all 3 of these reactions, we're not changing the concentrations of the actual substances in the equilibrium mixture. What we are changing is the value of the equilibrium constant because of how we chose to write the reaction. All right, here we have 3 different equations. Let's see how they are related. The first one, products over reactants, so concentration of NO squared times concentration of Br2 divided by concentration of NOBr squared. Now in your textbook on page 621, that particular equilibrium constant happens to be 0.014. The next one would be written as BrCl squared divided by Br2 and Cl2. Again, these are concentrations, so molarity in brackets, and your book tells you it's 7.2. So if you took the first 2 equations and you added them together, and you cross off the bromine on both sides, it would equal the 3rd equation. So NO, concentration squared, times BrCl squared, divided by NOBr squared and Cl2. How do we manipulate these 2 equilibrium expressions to give us the equilibrium constant for this 3rd reaction? Well, hopefully you can see you would have to multiply those 2 values of K together, and the bromine would cancel out, and you would have 0.014 times 7.2, which works out to be 0.10. So if 2 or more chemical reactions are added together, the value of the overall equilibrium constant for the net reaction is equal to the product of the equilibrium constant values from each individual reaction. And now we're going to summarize those 3 different types of manipulations by trying to get the 2 equations for which the constants are known. So Kp equals either 54 or 1.04 times 10 to the negative 4 power, to determine the value of Kp for this 3rd reaction. If you multiply the first equation by 3, the new value of K will be 54 raised to the 3rd power. If you flip or reverse the second equation, then the new value of equilibrium constant would be 1 over 1.04 times 10 to the negative 4 power. And if you add those 2 equations together, then you would multiply the 2 values of equilibrium constant together. And when you do that, you get an equilibrium constant for the net reaction of 1.5 times 10 to the 9. Section 15.4, Heterogeneous Equilibria. Do we include the concentration of either a pure solid or a pure liquid in the equilibrium constant expression? And the answer is no. And you can see on page 623, equilibrium exists between solid lead chloride and lead and chloride aqueous ions, but the equilibrium constant expression would just involve the concentration of lead ions and the concentration of chloride ions squared. But we do not include solid lead chloride in the expression, even though it does appear in the reaction and in the equilibrium. In this reaction, which is the decomposition of calcium carbonate to produce solid calcium oxide and carbon dioxide gas, only carbon dioxide gas is going to appear in the equilibrium expression, so whether that's a pressure or a concentration. You can see this on page 623. So as long as we have a certain amount of solid calcium carbonate and solid calcium oxide, the pressure of the CO2 is the same in either example. All right, let's take a look at some examples where we have to write the expression for Kc and eliminate pure solids and pure liquids. So we have concentration of CO divided by concentration of CO2 and concentration of H2. We eliminate the pure liquid water. Here we have concentration of CO2 squared divided by concentration of CO squared. We eliminate the solid tin oxide and solid tin. In our next example, we can eliminate the solid chromium and the solid silver. So concentration of chromium 3+ divided by concentration of silver cubed. Then finally we eliminate the pure liquid water. So we have concentration of ammonium times concentration of hydroxide divided by concentration of ammonia. Section 15.5, calculating equilibrium constants. If you know the concentrations of all of the reactants and products in a particular chemical reaction at equilibrium, you can plug in those values into the equilibrium constant expression and simply solve for K. However, in some situations you do not know the concentrations of all the species in an equilibrium mixture. As long as you know the initial concentrations of all species and the concentration of at least one substance at equilibrium, you can use stoichiometry and what I call an ice chart or an ice table to keep track of the amounts of each chemical substance. So ICE stands for initial, change, and equilibrium. And I will call these either an ice table or an ice box, and I might put the word reaction at the top and call that a rice table or a rice box. Sulfur trioxide is SO3. It decomposes to produce sulfur dioxide, SO2, and oxygen gas. So the balanced chemical equation looks like the following. Initially, we have a pressure of SO3 of 0.5 atmospheres. Initially, we have a pressure of SO2 and O2 of 0 because the reaction hasn't started yet, so there are no products. Over time, the concentration of SO3 is going to decrease, and I'm going to say minus 2x because the coefficient is 2. The concentration of SO2 will increase. I'm going to say plus 2x because the coefficient is 2, and the amount of O2 is also going to increase, but now it's plus x because the coefficient is 1. So we're doing this in terms of pressure, not concentration, but it's the same idea. So at equilibrium, I now have 0.5 minus 2x for my pressure of SO3. I have 2x for my pressure of SO2, and I have x for my pressure of O2. The total pressure in the reaction vessel at equilibrium is 0.65, and that's equal to 0.5 plus x in terms of the algebra. So if 0.5 plus x is equal to 0.65, then x equals 0.15. So that's my pressure of O2 at equilibrium. The pressure of SO2 would be 2x, or 0.3 atmospheres, and the pressure of SO3 at equilibrium would be 0.5 minus 0.3, which is 0.2. So now I know the pressure of all three gases at equilibrium. That rice table was very helpful to do that calculation. So now we can write the equilibrium constant expression. So products over reactants. We're doing this for Kp, so pressure of SO2 squared times the pressure of O2 divided by the pressure of SO3 squared. We can use this expression to calculate the value of Kp because we have the equilibrium values for the pressure of all three gases. So it's going to be 0.3 squared times 0.15 divided by 0.2 squared. And when we do that math, we get 0.34 for our value of Kp. Section 15.6, applications of the equilibrium constants. In our first row of this table, where it says, in which direction, left or right, should the reaction proceed in order to reach equilibrium? Well, it's pretty straightforward that the reaction would have to proceed toward the right because we have only SO3 and we have no SO2 and O2. So with only reactants and no products, the reaction would have to proceed toward the right. On the other hand, if we start with only products, SO2 and O2, and we have no reactants, it would have to proceed toward the left. Now in the next example, we have one atmosphere of all three gases. It turns out that that's going to go toward the left, but that's not obvious. So let's have to wait until part C to see why this occurs. All right, on to part B, define the term reaction quotient. So on page 627, they define the reaction quotient as a number obtained by substituting the reactant and product concentrations or partial pressures at any point during a reaction into the equilibrium constant expression. So the Q has to do with where you are right now, not necessarily where you are at equilibrium. Okay, let's take a look at the scenario one more time when you have one atmosphere of each of those gases. The value of Q would be to take one atmosphere for both SO3, SO2, and O2 and plug it into the equilibrium expression. So 1 squared times 1 divided by 1 squared is 1. Now it turns out that the value of Kp is actually 0.338. So Q, which is 1.0, is larger than K. Larger than K, Q is larger than K. What does that mean? It means you have too many products or not enough reactants. So with too many products, it's going to shift toward the left. In general, if Q is equal to K, then you are already at equilibrium. If Q is larger than K, you have too many products, so it's going to shift toward the left. And if Q is less than K, you have too many reactants, so it would shift toward the right. Here's another way of visualizing the situations with Q versus K. So if you're not quite at equilibrium yet because Q is less than K, then you'd have to proceed toward the right to increase the amount of products until eventually Q equals K. So if Q is less than K, you have too many reactants, not enough products. The reaction would proceed from left to right. If Q equals K, then you're already at equilibrium. If Q is greater than K, too many products or not enough reactants, the reaction proceeds from right to left. So Q equals K, you're already at equilibrium. Calculate the value of Q for each set of given conditions and then determine in which direction the reaction will proceed. So in the first scenario, it would be products over reactants like this. 1 squared times 1 divided by 0.5 squared. Q is 4. Q is larger than K, so too many products. It would have to shift toward the reactants, toward the left. Our next example, 0.5 squared times 0.5 divided by 1 squared. So we have a number, 0.125, which is less than K. Q is less than K. We have too many reactants. We would shift toward the products, toward the right. Now we're doing 1.83 squared times 0.909 divided by 3 squared. And we are already at equilibrium because Q is equal to K. All right, in this example, we have the equilibrium situation between hydrogen iodine and hydrogen iodide. In equilibrium, we know the concentration of hydrogen is 0.575 moles per liter. The concentration of iodine is 0.375 moles per liter. we know what the expression should look like. Concentration of HI squared divided by the product of the concentration of hydrogen times the concentration of iodine. It's equal to 50.5 at this temperature. We plug in everything we know and we solve for the one thing we don't know, which is the concentration of HI. So doing the math, it works out to be that the concentration of HI is 3.30 moles per liter. In this situation, we have hydrogen and iodine. So there's no product, there's no hydrogen iodide yet. Each of the concentrations is 2 moles per liter. So we have hydrogen, iodine, and we have 0 for the concentration of HI. The hydrogen will go down by X, the iodine will go down by X, and the hydrogen iodide will go up by 2x because of the stoichiometry in the balanced equation. So 2 minus x, 2 minus x, and 2x are the concentrations of each substance at equilibrium. Let's go ahead and solve using the expression and the fact that it is 50.5. We're not going to do the quadratic equation for this particular problem. We're just going to take the square root of both sides. And when we do the square root of both sides, we get 7.11 equals 2x divided by 2 minus x. We finish the math and we get x equals 1.56. So plugging that value for x into the final row of the Rice table, 2 minus 1.56 is 0.44. 2x would be 2 times 1.56, 3.12. So we now know the concentration of each chemical at equilibrium. All right, so here we have a scenario in which we have hydrogen iodide only. So the concentration of each reactant is 0. The concentration of hydrogen iodide is 2 molar. We fill in the information for the change. That's going to be plus x for each reactant and minus 2x for the product. Again, these changes are based on the mole ratio. And we go ahead and take the expression, which would be 2 minus 2x quantity squared divided by x squared equals 50.5. And again, let's take the square root of both sides. So when we do that, we get 7.11 equals 2 minus 2x divided by x. Finishing off the algebra and the math gives us x equals 0.22. So we can plug that value of x into the final row of our Rice table. So we get 0.22 for each of the reactants and 1.56 for the hydrogen iodide product. In the next scenario, all 3 gases were added to a flask and the concentration of each gas is 2 molar. So will this equilibrium be achieved by causing the reaction to shift toward the left or the right? We must compare Q versus K. 2 squared divided by 2 times 2 is 1, and the K value is 50.5. Since Q is less than K, the reaction should proceed toward the right to reach equilibrium. So now that can help us figure out that it's going to be minus x for the hydrogen and the iodine, and plus 2x for the hydrogen iodide. So we're going to plug those values into the K expression. 50.5 equals 2 plus 2x quantity squared divided by 2 minus x quantity squared. Again, let's take the square root of both sides. 7.11 equals 2 plus 2x divided by 2 minus x. And the answer is x equals 1.34. So plugging 1.34 into the final row of the Rice table, we get 0.66 molar for the equilibrium concentration of both hydrogen and iodine, and 4.68 molar for the concentration of hydrogen iodide at equilibrium. Section 15.7, LeChatelier's principle. In this diagram, you can see that there are various percentages for the percentage yield of ammonia in the Haber process. As the pressure is increased from 200 to 500 atmospheres, the percent yield increases. As the temperature is increased from 400 to 550 degrees Celsius, the percent yield actually decreases. As you can tell from Part A, an equilibrium system can be affected by various changes in pressure or temperature. LeChatelier's principle, which is defined on page 631, says the following. If a system at equilibrium is disturbed by a change in concentration, pressure, or temperature, the system will shift its equilibrium position so as to counter the effect of the disturbance. Suppose we have an equilibrium between A, B, and C, where the concentration of A is 1 molar, concentration of B is 2 molar, and concentration of C is 5 molar at equilibrium. So the value of K, the equilibrium constant, would be 5 divided by 1 times 2, which would be 2.5. So we start with an equilibrium constant of 2.5 at this particular temperature. They added more of substance B until the concentration became 4 molar. So now we have to plug in the numbers currently, which is 5 divided by 1 times 4. So we have a new number for concentration of B, and we get 1.25. Since Q is less than K, the equilibrium is going to be achieved by shifting the reaction toward the right. So Q is less than K. Let's go ahead and use our rice box and figure out what happens as the equilibrium is achieved. We're shifting the reaction from left to right. That's why it's minus X for the reactants and plus X for the products. So we have C divided by A and B. So 5 plus X divided by the product of 1 minus X times 4 minus X. And that is equal to 2.5, which was the original equilibrium constant. Now we have to do the math, which involves the quadratic equation. So when we do this math, we get two values for x, 0.4 and 5.0. So 5.0 is the nonsense answer because you can't have a negative concentration at equilibrium. We plug in 0.4 and we get 1 minus 0.4, which is 0.6, 4 minus 0.4, which is 3.6, and we get 5 plus 0.4, which is 5.4. So now we know the concentration of A, B, and C at equilibrium after the shift has occurred, after we added additional B to shift the equilibrium from left to right. So here we have initial set of conditions with 1, 2, and 5 when it was already at equilibrium. We disturbed the equilibrium by adding more of substance B, so we had 1, 4, and 5. And now the new equilibrium with concentrations of 0.6, 3.6, and 5.4. So in this chart or diagram, you can see that initially the concentrations of A, B, and C were 1, 2, and 5 moles per liter. You can see the point where additional B was added to increase that concentration, and then slowly it reached equilibrium. It reestablished equilibrium, and the concentration of A and B went down, the concentration of C went up as the reaction was shifting toward the right, toward the products. LeChatelier's principle can be understood by talking about shifting left or shifting right. If you add more reactants, it's going to shift toward the right, so toward the products. If you add more products, it will shift toward the left, back toward the reactants. If you take away reactants, it will shift toward the left to make more reactants to make up for that stress. If you take away some products, it will shift toward the right to make more products to counteract that stress. If there is a shift in the equilibrium position, but as long as the temperature does not change, then the value of K itself will not be changed. The only way to change the numerical value of K is by changing the temperature. When the equilibrium system involves gases, then the volume of the container can either be increased or decreased, and this may affect the position of the reaction. The equilibrium can be affected by that. So if you increase the pressure by decreasing the volume of the container, the equilibrium will shift toward the side of the equation that has fewer moles of gas. If you lower the pressure by increasing the volume of the container, then the reaction will shift toward whichever side has more moles of gas. So in this picture, you can see that we have 2 moles of A on the left and 1 mole of B on the right. So when the volume is decreased, it's going to shift toward B because there are fewer moles of gas. When the volume of the container is increased, it shifts toward A because there is a greater number of moles of gas. So that visual helps you see which direction the shift occurs. Explain why changing the pressure on this equilibrium system has no effect. Well, there's 2 moles of gas on the left and there's 2 moles of gas on the right. So changing the pressure by affecting the volume of the container would have no effect because each side of the reaction contains the same number of moles of gas. Here we have the equilibrium system we've looked at before in this packet. We start with 1 mole of gas, N2O4, and the products are 2 moles of gas, NO2. Now suppose that we have an equilibrium system already established where we have a concentration of N2O4 of 2 moles per liter and a concentration of NO2 of 0.65 moles per liter. 0.65 squared divided by 2, that gives us a value of 0.21. So you're already at equilibrium, and then you reduce the volume of the container by half. So that is going to double the concentration of each gas because the volume is reduced by half. So now instead of 0.65, the concentration of NO2 is double, 1.3. Instead of having a concentration of 2 for the N2O4, now that concentration is 4. If we solve for this particular value of Q, the reaction quotient, we get 0.42. And since Q is larger than K, we have too many products, we're going to have to shift toward the reactants. So shifting toward the left because Q is larger than K. So that means that if we're shifting toward the left, the N2O4 is going to change. It's going to go up, so 4 plus X, and then the NO2 is going to decrease, so 1.3 minus 2X. Remember, that's plus X and minus 2X. The change is proportional to the mole ratio in the balanced equation. So what do we do with 4 plus X and 1.3 minus 2X? We plug it into the equilibrium expression. So 1.3 minus 2x, quantity squared, divided by 4 plus x equals the equilibrium constant 0.21. We do the math, which involves the quadratic, and when we solve for x, we get 2 solutions, one of which is the nonsense solution. That's the 1.2. It's not possible to have a negative concentration equilibrium, so 0.18 is plugged in, 4 plus 0.18, so 4.18 moles per liter for the new concentration of N2O4, and then 1.3 minus 2x, that will give us 0.94 for the concentration of NO2 when equilibrium has been re-established. Another reason why this answer makes sense is that we have decreased the volume of the container, so the shift occurred toward the side of the reaction with fewer moles of gas. So that's why the N2O4 has increased and the NO2 has decreased. We shifted toward the side of the reaction with fewer moles of gas. What if we increase the pressure not by changing the volume of the container, but rather by adding some other gas like argon? Well, the total pressure might go up. However, the partial pressure of each individual reacting component would not be affected. So therefore, if you add more argon or more neon or helium, that would not cause a shift in equilibrium because the partial pressure of each of the reacting components would not be affected. Let's talk about heat, so endothermic and exothermic reactions. If a reaction is endothermic, we can treat heat as a reactant on the left. If a reaction is exothermic, we can treat heat as a product on the right. If the temperature of the system is increased, then the LeChatelier's principle says the system is going to respond as if we added more reactants to an endothermic reaction, or as if we added more products to an exothermic reaction. And it will shift in the direction that consumes some of this excess heat that was added. If we lower the temperature of the system, it is as if we have removed some of the reactants from an endothermic reaction, or as if we have removed some of the products from an exothermic reaction. And the system will shift in order to produce more heat to counteract that stress. This table summarizes those changes. So we have endothermic versus exothermic, and you can see the visual there with heat plus reactants goes to products, or reactants go to products plus heat. If we increase the temperature by adding heat, an endothermic reaction will shift to the right, and the value of K will increase. Remember, this is when you change the value of K by changing the temperature. If you add more heat, an exothermic reaction will shift to the left, and the value of K will decrease. What about removing heat or lowering the temperature? Well, if you remove heat or lower the temperature, an endothermic reaction will shift toward the left, and K decreases. And if you remove heat from an exothermic reaction, it will shift toward the right, and K will increase. So this table is a nice summary of the various directions of shift for endothermic and exothermic reactions involving temperature changes. You may recall in part A of this section, it was observed that when the temperature is increased for the Haber process to make ammonia, it caused the percent yield to actually go down. So that means that at higher temperatures, the value of Kp is actually decreasing. What does this say about the reaction for the synthesis of ammonia? Well, it says that the synthesis of ammonia must be an exothermic reaction because when the temperature goes up, it causes the reaction to shift toward the left, causing K to decrease. So by adding more heat, it's going to shift away from the products, so it's an exothermic reaction. In an endothermic reaction, heat would be absorbed. In an exothermic reaction, heat is released. So for an exothermic reaction, if you were to increase the temperature, it lowers the value of K. Finally, we're talking about a catalyst. This will affect the activation energy value, but it affects both the forward and the reverse reaction. So when you add a catalyst, it does not shift the equilibrium at all, but simply increases the rate at which equilibrium is achieved. You get to equilibrium at a faster rate, but you don't change the position of the equilibrium at all. Imagine an equilibrium where A goes to B, so A is a reactant, B is a product. The diagram at the right shows the change in the concentration of B over time. So B is increasing until eventually it levels off at equilibrium. One of these curves is the catalyzed pathway, and the other curve is the uncatalyzed pathway. Does the concentration of B change at equilibrium as a result of a catalyst being added? No. So that means that we're still reaching the same value, just at a faster rate. So the correct answer here for which one is catalyzed and uncatalyzed is the uncatalyzed reaction is slower. The catalyzed reaction proceeds more rapidly, but you still achieve the same value for the concentration of B. You just get there faster when you have a catalyst. All right, well, that represents the end of the Chapter 15 packet. I hope that those answers were helpful. Thanks for watching.